In this lesson, we will learn another test for testing the convergence or divergence of a series. The ratio test measures the rate of growth or decline of a series by examining the ratio a sub n plus 1 over a sub n. For a geometric series, we know that this ratio is a constant, and we know that a geometric series converges if and only if the ratio of successive terms is less than 1 in absolute value. The ratio test is a powerful rule that extends that result to more general series. First, we'll state the ratio test. We'll start with a series sum n equals 1 to infinity or sum n equals 0 to infinity of a sub n with positive terms, and we'll let rho denote the limit as n goes to infinity of the ratio a sub n plus 1 over a sub n. So when we're doing problems, we'll compute rho. If rho is less than 1, then the series converges. Note, though, that the ratio test doesn't tell us what value the series converges to, it just tells us that the series converges if this value of rho is less than 1. If rho is greater than 1, or if we get a limit of infinity, the series diverges. And if rho is equal to 1, then the ratio test gives us no information, and we'll need to use another test to determine whether the series converges or diverges. Note that the ratio test is particularly useful when we have series involving factorials or series involving constants raised to an n power combined with polynomial functions. The ratio test is not going to be helpful for p series or for any series that simply consist of rational or algebraic functions of n. Let's take a look at a few examples. In the first example, we have the sum from n equals 1 to infinity of n cubed over 5 to the n. So this is a series involving a polynomial n cubed and a constant raised to the n power. So the first thing we're going to do, we note that our series does consist of positive terms. So the first thing we're going to do is compute this value of rho. So limit n goes to infinity. We need to compute the limit as n goes to infinity of a sub n plus 1 over a sub n. So we will put in a sub n plus 1. That means everywhere there's an n, we're putting in n plus 1. So n plus 1 cubed over 5 to the n plus 1 over a sub n. So n cubed over 5 to the n. So now we'll do a little bit of algebra to simplify this expression before we take our limit. So we notice that that fraction in the denominator flips. So we end up with 5 to the n times n plus 1 cubed over 5 to the n plus 1 times n cubed. So 5 to the n over 5 to the n plus 1, that simplifies to 1/5. And now we're left with n plus 1 cubed over n cubed. So I'm going to write that as n plus 1 over n all cubed. So now we notice you should be able to compute the limit as n goes to infinity of n plus 1 over n. This limit goes to 1. Make sure that you talk to your instructor if you have any questions about how to compute that limit. And we end up with 1/5 times 1 cubed, which is just equal to 1/5. So our rho is equal to 1/5. Observe that 1/5 is less than 1, so we conclude that our series sum n equals 1 to infinity, n cubed over 5 to the n converges. Because by the ratio test, because our value of rho was 1/5, which is less than 1. So this example illustrates the key steps in using the ratio test to determine whether a series converges or diverges. We identify that we have a series with positive terms. We then compute the value of rho, which is the limit as n goes to infinity of a sub n plus 1 over a sub n. In this case, rho was less than 1, so the series converges. Again, note that the ratio test doesn't tell us what value the series converges to. We just know that the series converges.